afternoon, and thank you for attending. Today's presentation is called An Introduction to Laser Ablation and will be presented by Lucas Smith, who is our Director of Business Development for the Americas at CTEC and Photon Machines. We will be taking questions at the end of the presentation, so feel free to submit those throughout. And I'm going to go ahead and turn it over to Lucas.
Thank you, Shelley. Hello, good afternoon, and good morning to those of you attending from across the country. Welcome to today's latest webinar, which, as Shelley pointed out, was an introduction to laser ablation ICP-MS. This is a little awkward, as I actually allotted the first 5 minutes of this presentation for a rowdy standing ovation, but I've just remembered that I can't see or hear any of you, so we'll I'll just know that your applause is appreciated. And the good news is that we get to spend those extra 5 minutes learning about lasers. With that said, I advance to the next slide here. In theory, there we go. The goal today is to not only teach a little bit about laser levels of understanding from about lasers from those that have just been told by a friend that this might be advantageous for their lab and that they'd like to find a little bit more out about it, all the way to people that quite frankly know a lot more about the technique than I, and then of course everyone in between. In addition to that, I want to tell you just a little bit about CTEC, the company, and what we do. You'll see here on the slide this lovely picture of Teledyne CTEC in Omaha, Nebraska. It looks a little bit ominous. You can almost see the tornadoes in the background, but it's a beautiful facility. And as far as the company goes, we joined Teledyne in August of 2013, which has been really nice, as it's helped us a lot with our focused investment on R&D. Essentially, once joining the Teledyne family, it helped us a great deal as we had access to a number of technologies that previously we weren't able to have that access to. So specifically, you know, there's one Teledyne company in particular that makes cameras that can read business cards from space and that sort of thing. So having that access has been a huge benefit to us. As I mentioned, we are located in Omaha, Nebraska. We're about 80 strong. And while we do a lot of laser ablation work between CTEC and Photon Machines, which is based out of Bozeman, Montana, we're actually known as the world leaders in sample handling and sample introduction, specifically auto samplers. Most of you, assuming that you work in an organic lab from time to time, probably have a CTEC auto sampler in your lab. Sometimes it might say thermo or Agilent or something else on it, but more often than not, it's built right in Omaha. So today's presentation with CTEC, already discussed, is going to focus on laser ablation. I'm going to go through a lot of things, starting with the most basic. What is laser ablation and why would we use it? Moving on to a brief, I promise, history of laser ablation. And then we'll go on through a lot of the important factors that determine exactly how we want to do it, what is the best way to go about it for your specific application. And then towards the end, we'll also address some applications so that you can get a feel for the use of the technique. So here's the most obvious question. What is laser ablation and why? Well, it is the removal of a material by interaction with a high energy laser. You can think, you know, traditionally the analysis, inorganic analysis by ICP is done by a dissolution step where you take your sample, dissolve it in acid, and then introduce it to the torch. Using laser ablation, you forgo that dissolution step, and because of that, you get a couple of nice advantages. One is that you don't need the acids, you don't need a hot block or a microwave or anything along those lines. The sample prep, not to say sample prep isn't necessary, there are still some portions of that to the technique, but it varies quite a bit based upon your sample. The other advantage is that you're able to retain spatial resolution. So if you think about having a sample, it could be anything, maybe it's a microchip, just as an example. And once you dissolve that in acid and introduce it to the plasma, it simply is what it is, and that being a homogeneous mixture, as opposed to analyzing it by laser ablation, where you might be able to ablate one corner and then another and be able to tell exactly what the elemental composition is of the sample at those specific points. That, of course, extrapolating that out can lead to beautiful elemental maps that we'll show you some examples of as we go forward. So this here is a very simple schematic, what we would be looking at in laser ablation. So over to the left, you'll see that this is simplified by basically showing the entirety of the laser as just the left portion here. You'll see where the slide shows laser, IR or UV. That's where we're generating the light beam that is then bounced through the optics down into the sample chamber. That's a gross oversimplification, of course, of what's actually happening, but I promise to expand on it a little as we go through. We'll then use a sweep gas to take the ablated sample, which we sometimes refer to as the analytical plume, and sweep that directly into the plasma. Of course, it's detected. Okay. This now is a little bit more information about the laser portion of itself. You'll see in the bottom left-hand corner of the screen, the laser or light engines, it's sometimes referred to, that generates the beam. It comes from there and goes through a shutter that we have the ability to open or close for the analysis, and then it begins to go through a number of mirrors and optics. There's a couple of points in particular, specifically the homogenizer and aperture, that I'll discuss a little bit more as we go forward. But in the end, that laser beam goes through all of those components and eventually strikes the sample in the sample cell, where the analytical plume is created and goes out to the ICP. Now, a couple other points of note here is that the camera that you see at the very top, we're able to engineer the system so that your camera view is directly above the sample itself, which is very nice. And in that way, we're also able to add the rotating polarizer and 3 different kinds of light positions that we can shine to this sample, which ensures that you're able to have good imagery, regardless of the sample type. Some samples are very clear and require a different type of lighting than maybe a solid, bulk metal analysis, as an example. So by use of the polarizer and the different light types, we're able, therefore, to give you the best imagery possible. Yeah. Very simply here, the reason I include this slide is just to show you the laser is typically set to the side, just to the side of the ICP-MS. Ideally, we keep the tubing length as short as possible, so that we don't have the opportunity for what's called transport fractionation, which I'll address just a little bit further on. The laser shown in this appears to be what we call the LSX-213. It's one of our laser types, which actually comes on a cart, allowing you to position it close to the ICP-MS easily. We have a number of floor-based models as well that just push on over to it. And now the brief history that I promised you. I swear I'm not going to read the entirety of the slide, but just wanted to point out a couple of things in particular. One, the technique really started to take off in 1985. And as you look down through the notes associated with it, you'll see a trend. Specifically, if you look at the 1987 demonstration of a 1064 nanometer laser, you'll see that wavelength continues to decrease as you go down through the history of this, where you have the 1064, and then at 93 through 95, you had the introduction of a 266 nanometer system, and then where everything starts to progress to 213 and 193. I'll get into the reasons as to why that's advantageous and why we've seen that trend as we go through this, but I just kind of wanted to point out the timeline and history in which that's occurred. Now, speaking of the different laser types available, we're looking here essentially at the family of CTAC and photon machines lasers. There are a number of them, even a little bit more than is displayed here as the fusions in the bottom right-hand corner. There are 2, a CO2 laser and a diode laser. We do have a 213 laser that sits above it, and then the lasers to the left are our excimer lasers, which operate at 193 nanometer wavelength. Okay, so what exactly does laser ablation look like now that I've told you what? This is just a very, very short video clip that gives you an idea of what's actually happening on the surface of the sample. That was anticlimactic, to say the least. Let me try that one more time. This would have been a very short video showing you what the ablation looked like at the surface of the sample. I'm not sure why I can't get the video to play. I apologize for that difficulty. But if you were to see this actually go through, what it looks like is a bulk metal sample here, and then we're scanning through this. So we're going to ablate a circle, obviously. These are circles on top of one another, and this would come on down, and then because we asked the system to give us a raster of the sample, what you would have seen is a serpentine analysis, where this would come all the way down and then down a little and then back over, giving us a long ablation of the sample's surface. I apologize for not being able to show that. That being said, we're happy to make the presentation available to anyone that would like to request it afterwards, and I'll be sure that that video is included in that if anyone would like. Okay. So I mentioned earlier that I would get into a little bit of the differences in lasers and exactly how the wavelength of the system is important to it. Typically, the lasers that we sell are broken into two categories. We refer to them as YAG, or solid state lasers, which include the 266 nanometer system before we discontinued it. I'll address that in a moment as well. The 213 nanometer system, and then once we go down to the 193, that's what we refer to as the excimer lasers. Now, if you remember the history slide that I showed just a few back, where I talked about the trend from 1064s all the way down to 193s, that's something that has really defined the market for those of us in the laser manufacturing world. Basically, every time a shorter wavelength laser comes out, everyone decides that that's where they need to be because they're getting such better results out of it. That got to such a point that the 266 system in particular was really only used for a bulk metal analysis. And because the cost of the lasers have come down, most people had just moved to the 213 because the resultant data was so much better. And as such, we recently discontinued the 266 altogether. It makes things a little bit easier when tailoring the laser discussion. Now, how do those wavelengths matter? Well, specifically, the narrower the wavelength, the better the coupling efficiency to transparent or translucent materials. So if you're trying to analyze something such as quartz, you really need the narrowest wavelength available to you. You'll see at the image to the right, the chart to the right, the transmission efficiency, where you can tell right away that the 193 to the far left there, excuse me, is being transmitted a lot less. When you talk about the absorbance in particular, only about 20% of that energy would be absorbed at the 266 wavelength. That goes up to 50% for the 213 and is over 90% for the 193. So because of that coupling efficiency, because the 193 works so much better with transparent or translucent materials, it's essentially the need for anybody doing that kind of work, and it's become the absolute norm within specifically the geochemistry market. Now, continuing to talk about wavelength, we looked here at a couple of craters. On the top, those are craters produced by a 266 nanometer laser, and then down below a 1064. That 1064 laser is really intended to heat, as to where heating is something that we're trying to actively avoid in most analyses. There actually are some benefits to it in very specific markets. But you can see here as we ablate a NIST glass with both. On the top, we're showing what we refer to as a catastrophic ablation. It's just very explosive, for lack of a better term. Basically, it blasts a giant hole in the surface, and you end up with large particles. You end up with inconsistently sized particles, and then, of course, you can see from the crater itself, it's hardly well defined. As you look at the 1064 laser result down below, you can see from the edge of the crater that there's been a lot of melting there, which is not ideal. As we look at the next slide, we have a comparison of the 193 to 266 as it relates to the crater shape and crater depth. Now, with the 193, you tend to ablate less material. So the crater isn't quite as deep. Of course, if you wanted the same depth, you can just ablate multiple times at the same spot. So it's not as though that's a disadvantage. It's actually an advantage because you have a lot more control over it. And as you look at that, as you look at the image to the right, you can see that the 193 is a far more consistently bottomed or flat bottomed crater, as opposed to the jagged edges and jagged bottom that results from the 266. You can also tell from the 266 that that you have kind of a tapered shape to the edge of the crater, which is also not ideal. In a perfect world, you would result your resultant crater would be a beautiful cylinder going straight down, no taper to it at all. Okay. The other laser that was shown a few slides ago when I showed the photon machines and CTAC laser family was a femtosecond laser. Here we're talking about pulse duration. And these images, I think, do a really nice job of showing you that advantage. If you look at the what we typically sell, the nanometer laser on the top, you can see the resulting crater, and on the bottom, the beautiful cylindrical crater that results from a femtosecond system. Now, the obvious question in that discussion would be, well, why aren't all systems femtosecond based? And that all really comes down to cost. You're looking traditionally at probably a doubling of cost or thereabouts to be in that femtosecond range. It should go without saying, but I'll mention it anyway, that from the fusion systems all the way to the femtos that we produce, there's a pretty significant difference in capability, in price, in need. Some of them are just simply very market specific. Okay, and then another image here of a crater. You see the beautiful edges that are provided by it. Okay. You'll see the title of this slide also. The ideal craters indicate controlled fractionation. That gives me the opportunity to introduce the concept of fractionation, which, when defined in its simplest terms, is basically when the composition of a material measured at the detector is not the same as the composition. So you're introducing some form of bias. What you see down below there then is that with high fractionation, what you tend to get are very large particles, a significant difference in the size of particles that are ablated, and that they differ in mass and volatility, as to where in an ideal world you have exactly the opposite. There's a couple types of fractionation. Transport fractionation would be one of those where you tend to lose part of the ablated material in the lines that lead to the plasma. It's one that I mentioned earlier and promised to expand on. It's the most significant reason that when you're building a laser, you want to take it into consideration and ensure that you have as few bends as possible in your line, that you have the shortest tubing lengths that you can possibly get, and you also have to take it into consideration with the flow dynamics within the sample chamber itself. The second type of fractionation is the in-plasma fractionation, and this is where the number of factors that I showed earlier about particle size really comes into play. what this is attempting to show is that if you have the larger particles, you need to make sure that they're as small as possible. Otherwise, you have that possibility of having different elements essentially trapped among others, which leads to that bias in signal. If you have smaller particles and particles that are consistently small, then you end up with a much better picture of the sample's actual makeup. So how does wavelength affect particle size distribution? Well, here we have a number of analyses showing the particle size and how, when using the 193 in the vast majority of cases, you end up with a much better particle size distribution, more consistent. And then finally, the last thing that I wanted to show you with regard to fractionation is just how it relates to each of the lasers. I'm obviously not going to read this table in its entirety to you, but you'll see a trend there where the heating effect that we see is reduced along with wavelength. Similarly, your coupling efficiency increases as the wavelength decreases, and you end up with a better particle size distribution as well, leading to far less fractionation on the lower wavelength lasers. So with all of that in mind, the ideal laser, if we were generating it, would have a short wavelength, a short pulse width, and we would have a homogeneous energy density. That homogeneous energy density comes from something called a homogenizer. I pointed earlier to the component when showing the schematic, but I'll do it again here in just a moment when you can see it actually within the laser rather than in a schematic. The next question is, what is the impact of a sweep gas type on fractionation? I've had a lot of conversations about this through the years where people don't assume that there's going to be much of an effect, but by varying between argon and helium, you can see quite a difference, as is displayed here. What you're looking at, these rings or halos around the actual crater itself are caused by that heating effect, and because helium has such a higher thermal conductivity, you end up with a greatly reduced effect there. And that takes us to a really fun part of the conversation, which deals with sample chamber types. I'm going to show you a great number of cell designs as we go through this. I'm going to do it very quickly because, frankly, I only have a half hour, and I could probably give a 3-hour presentation on lasers if I was given the time. So with that said, when I'm referring to a sample chamber, I'm referring to nothing more complex initially than the chamber that actually holds your samples and that we'll be ablating the sample into. Okay. So we looked at some examples of sample chambers that have been used over the years. You can see there's quite a bit of variance in them. There's 2 more. Another set. Now, when I say problem with small cells, what I'd like to point out is essentially there's an interesting dynamic in sample chamber size. Specifically, big cells are good because you can put a lot more in them, but there are also downsides to that, which I'll show in the next slide. With regard to small cells, you have a significant advantage with small cells because the volume of it is reduced, and therefore there's a lot less volume that needs flushed into the plasma. Because remember, our goal is to ablate the material, have that material go up into the analytical plume, and then have that swept into the plasma. But in order to do that, we have to sweep the entire volume of the chamber, ideally, into the plasma. So by having a small volume, it's easier to do that. But of course, if you look at the dime that's presented here for a little bit of size comparison, once you get to a small enough chamber that you're able to take advantage of that, you're now not able to put much in there. For some samples, size of the dime is completely fine, but there are other applications which sometimes require much larger samples. So big cells must be better, right? You can put a whole lot in there. But on the downside, we now have to flush that entire volume out, which takes a more significant portion of time. But you also introduce some challenges with regard to the flow dynamics of the entirety of the sample chamber. There have also been some other sample types or sample chamber types through the years, including a teardrop cell type. But the one that has really taken over in the vast majority of applications is a 2-volume sample chamber. So what do we mean by that exactly? Well, I'll show you the actual picture here, and then I'll come back to this slide. This is referred to as the Helix sample chamber. It is the sample cell that is used on the vast majority of our lasers, and its design is intended to give you all of the advantages of a large cell, being that you can place a lot of sample material into it, with all the advantages of the small cell, being that you can move the ablated material into the plasma as quickly as possible. So how do we do that? Well, what you're looking at here is the sample chamber from the top, where there's 2 different volumes. If you look at the entire brass outer portion of the chamber itself, that represents the external volume. But if you look at the arm that comes into the sample chamber from the bottom left, at the end of it, it has a cup. Okay, that cup actually sits over the sample itself, and we ablate down through the center of it. And the ablated material then enters the cup, and it's swept in down through the arm. So that's how we get that dynamic that I mentioned earlier, where you have the large outer cell, which can hold a great number of samples, but the way that we're able to take care of the volume challenge is that we only need to worry about sweeping the volume of the inner cup itself, which is much, much smaller, obviously. And coming back then to this slide, what should a 2-volume cell do ideally? Well, first is that it needs to efficiently remove as much ablated material as possible to enter the plasma. Remember, the amount of ablated material essentially equals signal or intensity, sensitivity then with the ICP. So we want to make sure we can get all that material in there. We also want to make sure that we produce the same transfer efficiency and fractionation characteristics, regardless of the ablation position in the cell. Essentially meaning that if we ablate a sample in one corner and then we ablate a sample in the opposite corner, we need to make sure that we're not introducing a bias based upon our cell. We need to be able to trust that data. And I have some data that I'll show you here in a moment that shows exactly that. We also need to allow large samples or many samples to be placed in the chamber, as nobody wants to open it up to place new samples all the time. It's very time consuming to do so. And we want to make sure that it can purge quickly and does not leak. All pretty obvious, but that's our goal in the development of this system. We worked with Australia National University, ANU, in the development, and we have exclusive rights to this cell, which is, it is the most peer-reviewed sample chamber on the market today, which is something that we're very proud of, along with its flexibility, which I'll talk about as we go forward. One of those ways in which we provide flexibility with the cell is, if I come back here to this picture of it, you'll notice that in the very center, what the sample cup is sitting over is what we call a drawer. These drawers are interchangeable, so you can place one and pull it out, put another one in. So a great number of our customers have more than one, so that they can do these. The one in the top left-hand corner is what we call our standard sample holder, specifically because it allows for the holding of 4 petrographic slides. It also holds 3 1-inch rounds and 2 half-inch rounds, which are typically used for your standards. We have another couple of options for that. We also have one that basically holds 9 1-inch rounds and 4 half-inch rounds. We call it the 9-hole drawer, which maybe we need to work on the marketing of that name just a little bit. But it's intended for nothing more than that. A lot of our customers are doing nothing but 1-inch rounds, so this makes a lot more sense because they're not wasting 2/3 of the sample drawer on the thin sections if they don't ever use them. We do also offer a cryo drawer in the event that you're doing tissue samples or something of the like. And then we have our most flexible drawer. We simply call it the open drawer. It is a height adjustable shelf that has, it's basically open. You can put whatever you want in it. So again, if you're doing zircons or something similar, then the 1-inch mounts make perfect sense. But if you were working maybe with archaeological samples and you have pottery shards or something that you want to place in the sample chamber without breaking them or mounting them in an epoxy, then you would want to do that with the open sample holder. A lot of customers simply put a small amount of putty in the bottom and then stick the sample right in that, which holds it perfectly in place. Some even use a label maker in order to put a label together to tell what that sample is, pottery shard number 1, or perhaps something more creative, and then put that right in the sample chamber along with it. Now, with regard to the another one of those aforementioned points, that you have to be able to trust the data for all corners of the sample chamber, so you're not introducing an additional bias. This shows exactly that. This work was done at the University of Arizona, for those of you familiar with the Geochron lab there. And it shows that you have remarkable consistency between all places within the sample chamber. Now, I've spoken on this a couple of times as we've moved through, and I promised to address it in more detail. But washout speed. For anybody that's looked into laser ablation in the past, this is no doubt something that's come up in conversation. Washout speed is the amount of time that it takes to flush the sample into the torch, out of the sample chamber and into the torch. And you want to keep that as low as possible. The Helix cell, when it was introduced into the market a washout time that was around 600, 700 milliseconds. And because that was under a second, it was actually a pretty substantial advancement in washout times. It's still a very strong, one of the best washout times on the market today. We do have some things that we can do, including a product that I'll discuss in a little bit called the Eris, which is able to reduce that pretty substantially. The one thing that I do want to point out here is this bottom point. The Helix 2 is truly tunable to suit all applications. So there are some cells that have been developed with the intent of making them application specific. Maybe they go really fast or they go really slow. The Helix gives you the advantage of being able to tune that, so you can essentially decide how fast or slow you want to go, which is how we refer to it as that tunable catch-all for applications. The inner cup that I discussed before, this is a little bit more detail of it. This is the cup that sits directly over your sample and that you ablate through. It introduces washout to 0.1% in less than 700 milliseconds, and we have the ability to add what I referred to earlier, the Eris, in order to get under 50 milliseconds, and frankly is often able to get down much slower than that, and we're able with most geo applications to get under 20 milliseconds, which we're very proud of. This is a basic schematic of what we're talking about there. The Eris in the upper right is really nothing more, not that I want to undersell it, but it's a stretch of tubing with a very narrow ID and a proprietary mixing bulb that attaches directly to the ICP-MS torch. And because it's a straight shot to the torch, you're able to reduce that washout time, like I said, is as low as sub 20 milliseconds. A pretty substantial advancement. One thing that is really nice about the Aeris in addition to that is that it allows you to remove it if you have an application where you didn't want to use it. Remember that earlier in the conversation we discussed some applications going fast is great, and others it might not be advantageous. In this case, you can replumb in 10 to 15 minutes. It's very, very simple. So you can take it out if you need. And by using it, you're able to resolve individual pulses, as you see here with University of Ghent data that was provided. So on the other side, the opposite of the Aeris, if in some applications you want to go much slower. Specifically, I would talk about depth profiling in that way. And what you have here is what we call the squid. Again, very basic, easy to add or remove in order to greatly increase those washout times. What the squid is doing is it includes a significant number of stretches of tubing that are all of different lengths, and it allows us to essentially separate the effluent and then put it back together, and in that way it smooths the data quite a bit by going much slower. Now let's show some images of the actual system itself. This is the laser without its covers on. You can see at the top, you can see an open tube. That's where the light will be flowing. I shouldn't say flowing, but going through. It is covered just simply to ensure that nothing gets in the path. And then here you can see the same view from the top. At the very top of your screen, you can see there's an annotation for rotating zero order diffractive optical homogenizer. I mentioned earlier in the discussion that I would show this in more detail. What this does is actually takes the light that comes into it and it breaks it up into a full spectrum of light. It diffuses into a number of other rays and then puts it back together. And the reason that you want to do that is that if you shoot a non-homogenized beam at a sample, the beam isn't even in that it can have hot spots and cold spots. What you more often than not see is that in the very center of the beam, it burns hotter than it does on the outsides. And because of that, you can get that tapered look that we talked about earlier. So by homogenizing the beam, you have no hot spots, no cold spots, and it makes it much easier to get a better shaped crater, one that's more cylindrical. Okay. You can also see that there is a positioning mask shown there. That is kind of like a slide rule that moves back and forth in the way of the beam. And by doing so, it has a number of different holes within it that allows you to shape the beam and select between maybe a 20 micron circle or a 50 micron square, or any of the other options. Here is a list of the spots that are available. They include circles, squares, crosses, and long rectangles. We also have a product we call the Analyte G2, which has a demagnification option, which allows you, instead of going to a maximum of 155 microns, it allows you to go all the way to 250 microns using the demag switch. And if there was an application that requires it by use of a custom mask, we can actually go all the way to 400 microns. So very, very large in size. You very seldom require that. In truth, the vast majority of customers tend to use spots between 10 and 50 microns, and probably even the majority of those between 10 and 30. There are some other options available. Here you see the reference to a dynamic aperture, or sometimes referred to as an XY theta. It allows you to work with very small 1 micron iterations to go between 5 and 150 microns in size, and also allows you to rotate. So essentially it provides you with it's not really unlimited, but a enormous number of options. Just to give you an example of what a lot of those tend to look like, there's some beautiful imagery that was taken at Cambridge. Okay. I realize that I'm over on time, so I'm going to go through the applications fairly quickly. There are a vast number of them. They range from the earth sciences, which is where we tend to see the majority of it. See a lot of dating work, a lot of zircons. Forensic work, we have some applications notes where different glasses or paints were analyzed in order to solve crimes, which I find extremely interesting. Archaeology, I've already mentioned, pottery shards and the like, and so on and so forth. We're definitely seeing a lot of growth in the biological and medical portion. A lot of tissue being analyzed as of late, including one lab that I visited just a couple of weeks ago, looking at brain tissue for concussion studies. Very, very interesting work. I'm going to skip the slide. So here's an example of where this can come into play, show you some really neat stuff. This, in this case, is a northern horse mussel that's been grown. We're looking at its shell. And the reason why is that when the shell is growing, it has the ability to uptake calcium as opposed to magnesium and back, or vice versa, based entirely, the rate of that exchange is based entirely upon the surrounding sea surface temperature. Okay, so assuming that the salinity remains constant, you can look at the ratio and tell a lot about the temperature history of the body of water. So if we go through, when we were to lay scans on top of this, you'll see it's going to analyze left to right and top to bottom. What we end up with is a pretty image that looks like this, in this case showing the single element calcium. But we can also do look at other elements, including strontium and magnesium. And here, if you were an environmental chemist, you were looking at that magnesium uptake, you could tell a lot about this, and you could actually do the math and determine the exact level, temperature rise or fall based upon that uptake. So in that way, it acts kind of what most of us who don't do this for a living think about, the information we get from ice cores or the like. At geological samples, I love this slide because it does two things. One is it shows you the imagery that often results from the analysis of zircon or similar. But two, it also shows just how far things have come in just the last couple of years with regard to the spatial resolution we're able to create by use of the ARIS. So if you look at these crystals on the bottom, you can see what I would refer to as a very, very pixelated image on the left, just because of what is now capable following the development of the ARIS. Gone essentially are the days of extremely pixelated imagery, if you'll forgive what sounds like a little bit of sales rhetoric. I mentioned we're also able to do work with tissues. So here we're looking at human tissue. You can see the stains on the left, and then on the right, very high resolution images that are that are element specific, and a lot can be read into that. We can also use this for a lot of other applications within tissue analysis, including this. This is cisplatin is a cancer drug, and in this case, we're looking at platinum concentrations, and you're able to tell exactly where that uptake occurred, which can give a great deal of information to the researcher. We also have the ability to do depth profiling, as I read before. This in particular is just a piece of glass that has a very small chromium layer within it. And if we ablate down through it, forgive me, my slide was a little out of order, but is the corresponding data. So in this case, you can see left to right as we're analyzing through. You can see where we began the analysis of the glass. That's being the first red arrow there in the middle, before we get to that chromium layer and then begin analyzing glass again. What's of particular interest is that in that thin chromium layer that we basically drilled down through, you can see a spike of gold right through it. So we can actually identify a gold contamination within it. Okay. Now catching up. We're also out of the software that we've developed within the system. Software, I can't stress enough the importance of software because, for a number of reasons. One is the sheer power of it, making sure that it's capable of doing everything that you want to do as a researcher and being able to take the imagery that you generate from it. Because as we all know, it's often the images that are the attention grabber with posters and presentations rather than, unfortunately, the wording that goes with it. So being able to generate and take all of that information is huge. The other thing is that within your labs, you often have a number of researchers, and maybe postdocs and grad students, for those of you in academia, or just dealing with turnover outside of it. It's important that the software be intuitive enough that it walks you through things and helps you in the chore. That's a big part of this for us, is making sure that the software is helping you get there and isn't something that you have to work with. So we're very proud of the Chromium platform, which has been very well received in the market. We do also utilize it with all of our lasers now. Prior to that, we had a couple of different softwares that were used for the YAG systems and for the Exmers separately, but we've standardized on the better of the softwares and are extremely proud of that. Okay. And like I said, I know I've gone a little over. I apologize for that, but I'm thrilled to answer any questions that you might have, or any questions that we have time for. All right.